the World Health Organization has labeled misinformation as a major threat to pandemic control. By some metrics, conspiratorial theories generate more user engagement than more reputable sources such as the US Centers for Disease Control and Prevention. Understanding the characteristics of COVID-19 misinformation and how it can spread and propagate on social media platforms is of paramount importance to public health. Our paper focuses on misinformation found on Twitter. In particular, we are interested in the following two questions. First, how do COVID-19 misinformation tweets influence the structure and organization of discussions on Twitter? And two, what are the characteristics of COVID-19 misinformation that allow them to gain influence within these social networks? COAID, COVID-19 Healthcare Misinformation Dataset, was utilized in our study since it characterizes a large number of news, user engagements, and social platform posts about COVID-19 with validated truth labels. We used a wide range of data mining techniques on this dataset, from network analysis all the way to dimension reduction, to answer these questions. This is what we found.
To start, we constructed the network out of nodes and edges. Why? We wanted to identify the modularity of the network. That is, how strongly the network could be divided into modules. These modules can help identify regions of dense interactions and regions of lighter interactions. This would help us identify communities, which are tightly connected groups of nodes. The goal is that there may be patterns in the spread of misinformation identifiable through these communities. So how do we find the communities of the network? Well, there are two parts we need. First, the open-ORD algorithm inside Gephi will allow us to visualize the network in 2D. And second, the Louvain algorithm will help us identify communities inside the network. We chose the Louvain algorithm since it is widely adopted and fast to implement. In the graph, the nodes represent users and the edges represent interactions between two users. These edges have weights. If two users reply to each other 5 times, that edge has a weight of 5. With that in mind, we apply the Louvain algorithm onto the graph to detect communities. For context, using a high resolution coefficient should give us larger communities, and a low resolution should give smaller communities. In this case, one dominant community emerges, as well as several smaller ones that are each around the size of a single thread. Importantly, we see on the right that fake information is scattered within the communities, especially this dominant community. The misinformation is very entangled with the real information. It is not clustered together in any sort of meaningful way. And again, if we use a low resolution coefficient, we see that the pink, largest community is about 6% of the total nodes, roughly equal to the amount of fake information in the entire dataset. We see that the fake information is still scattered amongst the communities. No set of communities are dominated by misinformation. If we try various resolution coefficients and find the percent of users that gave real info within each communities, we see that the top 10 communities stay between 80 to 100% true information. In fact, the means all fall around 95%. This tells us that it really doesn't matter if we took the whole dataset and found the percent of users with real info, versus if we took a community formed with any resolution coefficient and found the percent of users with real info. There is no statistically significant difference between the two. The Gephi analysis revealed that fake information is not being detected as communities. Rather, it is spread out and lives amongst the real information.
We extracted various tweet factors from the COAID dataset to analyze relationships between features, misinformation, and retweetability. These include information on likes, retweets, date time, and sentiment, as well as user information including the description, followers, and friends. First, regression analysis was used to quantify relationships between tweet features. Summarized here are the R-square values from the linear regression. On the left, the relations in true information are shown. On the right, the relations between misinformation are shown. In both matrices, both features are not correlated, and the two matrices look identical. The one exception is between user follower count and user list count, where the relation is stronger in the true information than misinformation. This relation makes sense, since if a user's tweets are in many lists, this will increase their popularity.
In the case of Boolean features, where a feature is either true or false, like whether a tweet includes a picture, using regression doesn't make as much sense. So we conducted a t-test to find whether these Boolean variables had different mean numbers of retweets. Presence of a GIF, video, or picture on a tweet was associated with a significant increase in the mean number of retweets for both tweets marked as misinformation and those that weren't. However, the presence of a URL was associated with a lower mean number of retweets. Because these features are essentially independent of each other, we performed a linear regression in order to map a relationship between these tweet features and the number of retweets. We removed the number of likes on a tweet and the date-time variables, which don't really make sense to use in this context, which resulted in an extremely low R-squared value and a high mean squared error. Next, we conducted a principal component analysis on the relevant tweet features. PCA is one of the most well-known dimension reduction techniques used to reveal underlying correlations that account for the largest variance in data. This technique was used in similar ways in various studies to investigate the structure of correlations between tweet features. Using the same dataset, the two main principal components accounted for approximately 42% of the variance. These correlation graphs show that within the top two components, the number of likes and retweets are directly correlated with each other. Furthermore, the number of followers, friends, and listed tweets are correlated with each other as well. However, the number of followers or friends is not at all correlated with the number of retweets in the first two principal components, and the number of hashtags on a tweet and the sentiment value of a tweet are essentially non-influential. By plotting each tweet on a graph with the top two principal components as axes, we found that misinformation tweets are not distinctly clustered or separate from non-misinformation tweets. In order to continue to explore this result, we also employed t-SNE, a dimension reduction method, to visualize the dataset. An important tunable parameter that affects the results of t-SNE plots is the perplexity, the number of neighbors each data point is attracted to. After trying many different perplexities ranging from 5 to 100, which is a typical range of perplexities used, no distinct clusters of misinformation data points and non-misinformation data points were found.
Now for some discussion. When establishing any type of relationship, it is important to validate this finding across a variety of different tests and parameters. For example, if you notice a relationship using one method, how do you know that relationship is not just an artifact of that method? A relationship gains credibility if multiple tests and parameters suggest the same result. Now let's consider our first question. In what ways do COVID-19 misinformation organize in social networks on Twitter? Our study found that communities containing a large percent of misinformation were not noticed, regardless of the resolution coefficient used. And second, we noted communities across a wide range of resolution coefficients contained roughly 2 to 7% of misinformation, which is around the size of the total misinformation found in the dataset, which is at 6%. In other words, on a network scale, misinformation seems to be integrated in all communities in isolated pockets. Note that small anti-vaxxer communities report using Facebook and private group chats to spread misinformation rather than an open forum like Twitter. This may be the reason why we don't see distinct misinformation communities in our network analysis. Lastly, we must consider what these results imply. If misinformation and true information are very similar, automated detection and removal of misinformation from these platforms is extremely difficult. Although there have been some reports of algorithms identifying fake news on Twitter, these algorithms rely on either identifying highly populated tweets, categorizing media outlets as reliable or unreliable, or requiring large amounts of human labeling of data. In some cases, for some machine learning projects, there weren't professional fact-checkers used, but rather the researchers were annotating the data themselves. Its applicability as a tool for combating misinformation is still something that needs to be investigated. With fake information being highly interwoven with real information, the best first line of defense actually comes from the users themselves. Encouraging users to cross-reference important information and being cautious when retweeting something that looks suspicious can significantly help and has been recommended by other researchers. This seems like a good first step to fighting misinformation on Twitter.